All right, we'll get started with our panel session for this afternoon. Just a quick few reminders. Evaluation forms, please remember to fill them out. They are read rather studiously by the steering committee to help improve the process. Even after 69 sessions, we still can find places to make this a better experience. Once we get started, if you have a question, raise your hand, and please wait for a microphone to arrive by speedy courier so we can hear what everyone has to say. I want to thank the panel today for participating in the panel and giving us a really great session this afternoon. I almost feel like it's safe to say we kind of have a quorum here right now in terms of what's really going on in QC right now. So that's kind of cool. So any agreements that we reach here today can become official dogma because we've got all the right people in the room. And the big thanks is we had no planet-killing asteroid mentions or wildfires or earthquakes, which will allow me to sleep a little better tonight, to say the least. So thanks to that great session today, and hopefully we'll have a pretty lively panel session today. So please get your questions ready, and make your questions and your voices be heard. I'm going to take the moderator prerogative here and talk and bring up the first question for just about anyone who wants to throw out an answer. I was down at the National Science Foundation last week and giving them a little overview of what we were going to be talking about here today and such. And the question came up fast and furious about quantum computing infrastructure workforce development. The idea is, A, are there enough quantum computing people out there? Do you have access to the right kind of folks you need with the right kind of job skills to further your existing research agenda? And also, what is it going to take to develop a workforce that can really address all of the infrastructure areas that we talked about today? I'm really happy that a lot of folks have quantum computing access using these websites, but in some sense I still feel a little queasy that we're crowdsourcing quantum computing applications at some level. So if we could get some of the panelists or all the panelists to talk a little bit about workforce issues and what are some of the solutions that they think would need to be taken to make sure that we can fill all of the necessary niches in the QC stack with the right people at the right levels of qualification. So I don't know who wants to start. Carl?
So I'll speak from several different positions. One, the interagency process within the executive branch, we've talked about the workforce issue, and there are several problems, and I think most of the people here will admit to some of those problems. Until the last year or two, if you were doing quantum computer science or quantum information theory, unless you went to work for IBM, Microsoft, or Sandia, you basically left because there was no academic jobs in that area. And so until we could begin to get computer science departments to start hiring just one or two people, it really creates a crux because then you don't actually have that. The quantum engineering piece is coming up, and yet I believe there have now been several universities announcing new efforts in quantum engineering. There are others I know that are about ready to do that. I think that's another key component. We also, about a year ago, NIST hosted a meeting in which industry was there. I guess about 2 years ago now. And one of the questions that was coming out of them is that a lot of industry was telling us, well, we need a few evening courses so we can send our systems engineers back so they can learn to communicate with the physicist. And so this is a language thing. It's not a whole course structure, but one or two courses that allow those people who want to enter the field to learn the core capabilities that are necessary. The last thing is workforce growth. If the current rate of growth of people going into the startups and the big companies continue, the only way that can be maintained is that there are more scientists coming out. Now, again, I think in the end, there is a need for more PhD scientists, but ultimately there will be a need for master's and bachelor's level people trained appropriately. And that building out that infrastructure requires a lot of things going on within academia. I know I and some of my counterparts from the interagency committee, again, NSF, DOE, we have visited probably 10 or 12, 15 universities across the United States talking to deans and provosts and working that. But I think, should pass the phone on to somebody.
I think I was a bit surprised that the architecture community had a lot of closet quantum mechanics fans, people who had been interested in quantum computing, followed it sometimes as an avocation. You don't find many physicists, computational physicists or chemists, who are closet computer engineers or architects. But we actually need people who are interested in and can work cross disciplines in exactly that way. They have to understand each other, and it can't be just a one-way thing. I know there was one meeting where we spent 20 minutes before people really realized they were talking past each other. One group used a word, gate, with entirely different intent than another in the room was using the word gate. And it's amazing that could remain unknown to both for as long as it did. But there are many challenges in background that we'll have to learn to do. But I think we need to have that communication between the scientific community and the engineering community, and people who are able to work across it. Doubt will get people, very many, be a
I think I agree with probably everything that's being said here. I think I'm just following up. I think there's still need for PhDs. There's a lot of science to be done. One of the things we get at IBM is we get a lot of people from not quantum background. Getting them educated when we have people in quantum you can show that it can be done. It would be good, as you said, to have some way that people can go out, get formal training, and get retrained to understand the words. So I agree with.
So it was a bit easier than we feared to find people who know quantum, because there are many people, they are physics PhDs, then left academia, became architects, programmers, engineers, business people, and now we find them back and they still have their quantum background, and that helps get in. But what I find is that until recently, quantum computing was basically people building qubits and people proving theorems. And now we want to solve real problems, and that means we need people who know how to solve problems classically as well as quantumly. So we need to train the quantum people in HPC methods, and we need to train the HPC people in quantum methods. So that's for the education. And it gets hard by the top people being drawn to the industry, and there are many groups who want to hire postdocs in quantum computing who don't find candidates because IBM and we suck them up. And same with faculty jobs. But because of that, there are so many new students entering, which will soon fill the faculty jobs there once we have those faculty jobs. We need many more.
Just a couple of thoughts to add. So like Jay mentioned, we also have had a fair bit of success at Rigetti at training PhDs from other disciplines to be quantum engineers. One of the vacuums that we've encountered is that when you need someone with more bachelor's level training for software, for fabrication, for layout, these people are nearly impossible to find. And so I mean, you find plenty of enthusiasm, and you can harness that enthusiasm. And what we've done at Rigetti is started something we call the Junior Quantum Engineer Program, which is specifically has sort of coursework and formal training around developing these skills for bachelor's level students.
So yeah, I'd agree with a lot of the comments made already. I guess we've had some success. Of course, D-Wave is a company based in Canada, and there's a fair amount of quantum academic work in Canada, so we benefited from that. And given that we're building systems at scale, we've been able to attract a certain number of people who are already very competent and are interested in that aspect of the business. I would also echo what was said previously about we hire across the range from bachelor's, master's, as well as PhDs. And for that, we've done a fair amount of internships and co-ops and things like that, and that's been very successful.
So Carl and I share a lot of what he said. I would just add that the research program, one part of those efforts is training people right here on this table who started off. I think that's way to get experts.
Are there any questions from the audience as of yet?
Across the whole QIS thing, at any given time, we probably have over 100, of which probably about 70 of those are students and postdocs who will then go to either academic.
Of Rigetti's 100 or so employees, I would say that about 80 or so are what we would label quantum engineers.
We've grown a factor of 5 in the last 8. I can't tell.
Another question. One of the things, if you go to the supercomputer they started a few years ago, is they hand out these little decals that says HPC matters. And I always wondered if the period, next question, decal. But it does bring up the issue that this community has a hard time work with PCs. It seems that this particular sector right now perhaps facing a challenge, perhaps with magnitude of complexity, because the barriers to the problems are that much harder. How can this be better reach out to subject matter experts who could potentially be developers of algorithms, of applications, or at least help the quantum developers think about what applications would be most suitable for a quantum environment? How do we reach the people who we have enough trouble reaching? How do we?
So I'm not sure I understand your question. And let me partially answer it, or maybe partially misanswer it, and clarify my confusion. So there are lots and lots of disciplines that use classical computing fundamentally. HPC can sometimes be an odd offshoot of computing because, well, you have to have parallelism, you have to structure your program that way, and sometimes that's a pain. But so HPC is, I think, rightly viewed as more difficult than mainstream classical computing. if you think you need the performance that we all believe quantum computers will eventually deliver, you will need that whether you're mainstream or not mainstream. So for me, it kind of comes back to the original, the reason people work on supercomputers is because they can't get their jobs done any other way. And if that's the case, I don't think the motivation is going to be very hard.
I guess in some case the answer is there's a general sense that there are more and more participants of HPC, that it's hard to get them on. It's hard to find them, and it's hard to convince them it's worth the effort. Some of their workloads into if that's going.
So I'll give two answers to this question that are slightly different. I think one of them is the chicken and egg problem. And the chicken and egg problem is I think if there was a really powerful, even 1,000-qubit device, and you could show what the real impact was on just a couple useful problems, you would see everybody coming out of the wall because they were all trying to figure out how it's going to disrupt them. And in fact, I've been at several meetings where we have seen a set of companies that I'm kind of shocked that these companies. These are not the companies building this stuff, but companies who want to use and exploit this, from banking companies to finance companies to airplane companies to, and then they all have a reason that they're sitting there and think that this might be relevant to them. So I think that will be the first piece. I think the second piece of this I will come back to is just trying to understand. So again, going and talking to the deans and chairs that relate to computer science departments and say, well, why are you not hiring at least one person doing quantum information theory and quantum computing? And their response is, well, the field is growing so rapidly, I have this big need for AI, I have this big need for big data, I have this big need. And so they're looking at the stresses on them, and they said, and when is this coming? And again, that kind of goes back to the chicken and the egg, but they also, in some cases, they're not monitoring well enough to realize that things are changing, and so they're not making the investments that they need to do to educate a set of students and everything else. I think what's surprising is, those few places where they teach undergraduate courses in quantum information, it fills up with engineers, physicists, and others. I mean, the young people are enthused by this, and they're looking at it. What's happened is that the piece in the middle hasn't moved yet, but we also don't want it to move too quickly. We don't want to train and overcommit. You need to do this at a level that the pull and the push meet each other.
I think I'm also a little bit confused. Are you asking how do we get people to quantum?
I guess I'm saying, how do you get subject matter experts, say chemists, physicists, designers, come to and start to help out with letting the developers and algorithm people know this is what we'd like to see?
Yeah, it's a difficult question to get experts to something. I agree with that. So, a big part of why we put the open source out there was to allow others to explore, to see what can be done. At IBM, we're taking a very broad net. We have the open source project. We have the quantum network, which allows other companies that are interested to come, talk, say what they want, to work out where it fits. We're even bringing into that is a lot of education. I worry about going too fast to grabbing a chemist or someone like that, because we've got to make sure that it's focusing on understanding quantum potential rather than is it better now. And so you've got to find those right experts that want to go back and look at scaling and things like this. And I think the best way is just communicating and working out, as Jim said, how to talk the same language.
Right now, we have no shortage of interest. Many people coming saying, we're looking at it, we're hearing about it in the press, we want to know if it is going to be meaningful to us, which we respond to as best we can. They all realize that there is nothing that exists that can deliver results. And so I think what will move them from interest and curiosity, proof points of business value being delivered that will then motivate their investment, will immediately face the anticipate of how we empower them. It is they can't just have interest, move to commitment, and pick up their keyboard and start to code. So I think experts in various areas in simulation are at that stage of being very open. Our challenge now, first proof point, be ready to empower them. Right now, we work essentially one-on-one with experts. We provide the with people who are experts relates. But that's not a very scalable approach. It helps us immensely, but the broader question you're talking about, exactly how do we move them, curiosity, excitement to business results, have enough.
Yeah, so I agree. And others. What I want to say is that in the midterm, I think it will be students who learn quantum computing during their bachelor and master, who then going to Vegas, areas and become the new experts who also know quantum, and that will change it. Just like the computing thing entered the life sciences and the social sciences, so quantum will spread there as well. Until then, it's really intensive work one-on-one with customers and partners, and that's not scalable. I agree.
So I may be impatient, but I'm not willing to wait for someone to prove a speed up on some particular problem. The early history of computing is rife with examples of things that were proven to be useful before they had proven speed up. Sorting algorithms are an example. You can see many examples where we didn't know the asymptotic results when they first started to get used. So I think the answer today is actually outreach. Get people to encounter these machines, break down the barriers of mystery, show them that they actually are usable, and then they will encounter like what can and cannot be done. I mean, we see this every day with our users. That the first thing they try is way too ambitious. They'll try to run a million gate circuit and be like, sorry guys, it's not going to work just yet. But very quickly they self-calibrate and start actually doing things which are more in the realm of possibility. And so, at Rigetti we take other outreach efforts like organizing hackathons to bring people on site for a day and get them using our tools, using the system, building an actual project in 24 hours that can run on the quantum processor, and then we hope that out of this, this will show something new, something actually useful.
Anybody have questions out there?
I have a comment on this one. So if you look back into something like the early 80s, we had small computers back then, microcomputers and things like that. Quite a few people jumped on the bandwagon and started looking at how to code for these things. I'll give you an example from quantum chemistry. So quite a few of the problems were pretty intractable, and we started writing programs. And pretty soon you had supercomputers that were pretty much brought to their knees by quantum chemistry programs. So if you look at it from that perspective, it was the undergrads and the grads that took upon themselves the challenge of how do we use this new thing. So the perspective you have today, if you were to have some workshops or tutorial sessions or something like that at any of the society meetings, like say American Chemical Society, add on a little workshop that says these are the current problems that have been solved by the groups at Harvard, you know, H2 plus, H2, lithium hydride, beryllium hydride dimer. Those are sufficiently challenging problems that all of a sudden people's eyes open up and say, if that can be done, maybe there are different techniques they can use. So it's basically inspiring them from one field. You can do the same thing from material science. I mean, like you see on the D-wave systems, it's such an ideal system for spinizing systems, right? So if you see any class of problems that map onto a spinizing set, it's solvable. Look at the problem of binary alloys. It's solved by spinizing states, you know? So perhaps having workshops through selected domains of science and engineering might give you the footprint that's required to get the class of educated users you're looking for who have a quantum background or at least a bent towards solving. I'd like to hear from you guys if that might be one thing you might want to do.
So we already reach out and we've gone and worked with many universities and done it. We did these. If you got suggestions for more that can reach more, bring them up. I think a big part of the original motivation for putting a quantum computer on the cloud for the first people to use was so people could do it. After we did it, one of the first things I did was work with IQC, and they brought all their students in. That they went around in this program they call USQUIP to bring in all newly PhD undergrads and PhDs, and one of the courses was to play on a quantum computer. I think knowing the right ones to go to, and if we're missing them, you should let us know, but that's what we're trying to do.
So I think there's, not an academic, so maybe my perspective is not correct, but I guess my experience has been that people get interested in a new machine when some new capability is within some plausible time frame. And for different people, that means different things. And so I think there's been a lot of confusion among potential users of quantum computers as to when are they going to be relevant, performance relevant. And, you know, I mean, we all see, I'm guessing we would be in violent agreement that we all see these articles saying, oh, it's 1 year away, oh, it's 10 years away, oh, it's 6 years away, oh, it's 15 years away. Well, if I'm a chemist and I don't really know, what I probably do is I average all those together. I get is it 6 years, is it 12 years? And I say, that's too long. I'll come back when this is more reasonable. So, again, this is my view, perhaps not accurate. So that was one point. I think performance matters. Delivered performance matters. It does get people excited. It does. In general, that's what delivers new science, and so for academics, that's typically interesting. I also think, I mean, we have a couple results that we've started to talk about using our systems for quantum simulation. I'm not a quantum physicist. I don't understand them that well, but my understanding is that, and those were used, those were developed using lower level interfaces to our system that are not generally available, and but I think when some of those results start to get out, one of them was presented last month at the March meeting of APS. I think once those start to get out, we will, and my understanding is that those were at the state of the art for the particular science disciplines in which they were relevant. I think exactly what you're saying will happen, and people will say, oh, maybe I'm not going to get the ultimate performance today, but it's not 12 years away. And so maybe there's a threshold there where we have passed or we'll pass soon.
Am I allowed to disagree on some things?
I'm hoping, yeah.
Yeah. So I dislike this idea of trying to put a timeline on when something's going to come. It makes it seem like there's going to be one point. And it's important that we've got to get the people in to start to understand, even right now, what is it really about quantum? So, it's going to be a continuum. We'll look back and I think one day we'll say, that's when it really was. And I just dislike hearing things like, is it 1 year, 10 years? I would rather see people try and bring down them and say, at the moment, we got to engage with these people to understand in their area how this applies. And this is probably why I objected when I got asked the question in my talk, when will it be commercial? I don't know what people mean when they do that, because we put a fixed point on it. So I think already, right now, you have the need for some people that are at the level that they want to understand entanglement in these algorithms and how entanglement matters. It's really relevant for them right now. When we are at the level that we're going to beat, say, what people can do classically on something, I'm not sure, but there's a spectrum, and we've got to make sure we cover that all.
I like what you said, and the reason why you disagreed with that too. One of the things we've been thinking about, if you look at what you folks have spoken on, it seems like if you look at quantum computing purely from a homogeneous system, it's pure by itself. You have to run everything in the quantum space itself. But some of you folks have also mentioned hybrid, in the sense of using a quantum computer for looking at a more complex component. Perhaps if we had more examples or began to discuss that in a more public forum of how to couple classical computing with quantum computing, that might have a faster acceptance route, and maybe that might be the route to getting more people interested in this field, perhaps?
We're not exactly hiding that. That's something we talk about. I had 2 examples in my talk. We've worked with various of our collaborators on that model. And in my talk, I think someone asked a question that showed it. They didn't see that part of a slide. A quantum computer is not going to replace an ordinary computer. If you've ever run ordinary arithmetic in a quantum algorithm, you know that it's incredibly inefficient. And we did some acceleration work with Professor Troyer at ETH about improving performance of our qubit simulator by moving everything that was classical or could be classical into direct execution. But the work with QAOA and the VQE, and those are all hybrid algorithms that divide the algorithm. It's not even the fact that it's a coprocessor. It's the fact that the algorithm is operating on both to use the best of both. That is well known. Now maybe that isn't known widely enough, but every time I talk about it, I give that example, and the fact that it helps with this NISQ era, because it allows you to do useful things with circuits of less depth. So we do talk about it, and we point to it as a way in which we're going to get something valuable before error correction is perfected and we have the scale to support fault tolerance.
So I'll give a slightly different perspective that in some ways is a continuum in what was just said. if you look at it, the first use of the transistor was the hearing aid. It wasn't a computer, and integrated circuits were a long ways after the transistor came out, and yet everybody wants to focus on the most complex technology that we believe will come out of this. That is that quantum computer that will be general purpose and error correctable, and be able to go and solve those real problems. It will come, and yet. I think another way of looking at this and trying to ask when it will come and when we need to be prepared and how it's going to impact my business is to go back and ask, well, are there any useful applications for 5, 8, 10 qubits? And again, in this, we know what some of those applications are. Again, better clocks, other types of things. There's sensor technology and other aspects to it. The development of those sensors, improved sensors and things that go beyond the quantum shot noise limit and everything else help perfect the technology. And as that technology is perfected, you build more transistors on your little circuit, and you eventually get to the 49, the Intel first chip. I mean, but it was many years to get there, and that was what, 1972. There we go. I'm doing pretty well on this, but that is going to be a process, and the same one is this is going to be a process, and I think we do ourselves a disservice if we overpromise too early. I think there will be early adapters. These will be the people who will see it. Again, in the quantum chemistry community, Alan Asper-Guzak, basically a traditional quantum chemist who became interested in quantum computing. I mean, he's been one of the movers and the shakers in the field. I think there will be other people like this because they can begin to see and they want to be the first. Because there's two ways I've always said of getting your name up in the lights. You can be first or you can be best. And I know with me, I'd rather be first because being best is a lot more work than being first.
Yeah, I think it's even way more than just the simple algorithms like VQE. It's really important in some of the work that we do, and I know Matthias Troyer does as well, is trying to understand, can we trade classical resources for quantum? If I can actually use some classical resources to get effective higher number of qubit and then use my quantum as just a little bit on top, this is very exciting, and this is really, really hard research that we're putting a lot of effort in to understand exactly what, well, I joked and said the negative signs, when those negative signs really matter. And I think you'll see a lot more of trading resources as these systems go, and also the algorithms that are like this VQE or type where you estimate an update based on the previous one.
Yes, and not only will all methods in the end be hybrid, and the hardware is hybrid already, and most is classical, and will be more so, but just thinking about the quantum algorithm sometimes gives us in the end, purely classical algorithms. For example, when we worked first with D-Wave, we wanted to check out what does this machine do. And we heard claims that this machine is huge factors faster than the best classical method. And then we looked at it and we tried to understand it. And now we learned how some parts can be mimicked, which gave us new purely classical algorithms that are also factors of 10,000, so faster than what was the state of the art. So we get speed up already with 0 qubits. And when we add then 1 more and 2 more, that helps more. So just thinking about new paradigms and just thinking about might the intractable maybe become tractable makes you have new ideas.
So I did not mention hybrid during my talk, and it was solely due to time. We absolutely see that will be hybrid for the foreseeable future. I would even call out, and I don't think it's just a nice to have. So we have a tool called QBSolve that we open sourced January a year ago. So github.com D-Wave Systems. And it takes, I referred to it very quickly as a decomposing solver. It takes a big QUBO and pulls out a chunk of it that can run on the hardware, and then does that iteratively, blah, blah, blah. It's an algorithm. You can go there and learn about it. But it's not just the decomposition that's important. There are portions of the problem which are easy to solve, a relatively easy energy landscape to solve, and they're solved blindingly fast by classical solvers, and it's unlikely that our quantum processor will solve it faster in the near term. So even if we had a processor that was 1 billion times faster than our processor is today, it's probably going to be faster to solve it on a classical solver, classical processor even then. So it'll be important for us to understand the portions of the problem which are best solved in each place.
I think if you look at the field of classical computing, a lot of the algorithms and the best ways to solve problems have been developed by heuristics. And so heuristics in quantum algorithms is something that is just beginning to blossom, and to a large extent it is because of there's hardware around where people can go and try different approaches. And I think that is probably the way people are going to understand how classical data and quantum data interact in a whole algorithm, and how you could separate some of these things out to the best.
No, I just wanted to ask a question because, and you guys are all the experts. It's a fair question. But, we've talked today how, quantum computing is in its early stages, and we're just talking about the Intel 4. But at the same time, are there lessons learned from that could be applied to? And, hybrid computing could be one, but we have also gone through some of the pains. And if you look at HPC, even now, we have hardware and software experts who know about the system, and we have domain experts like physicists and chemists. But we also have this, kind of a glue, these people who are known as computational scientists. And so here we are talking about hardware experts, and we are talking about quantum algorithms and applications. But at the end of the day, these are user groups here. So we just have a application that we need to solve. And so the question is, and maybe, it may be just your opinions, is whether we should try to, have or build a cadre of, computational science, quantum computational scientists, people who know enough about hardware but also can work with the domain experts to kind of make that transition. We don't have to go through another 60 years like we did with high performance computing to get quantum computing. It just doesn't make sense. That's not how the world works. Because then in that case, Facebook and Twitter should have taken us 100 years. So anyway, just a comment on that. I'd like to hear everyone.
And again, one typically doesn't talk about another agency, but I mean, the Department of Energy, basically part of their effort in the last 2 years has been really to address the quantum computer science space. And again, if you come back in to their labs and everything else, I mean, again, they have people in the high performance computing community and everything else. And I believe part of their programs are being designed to engage these people early on to begin to address these questions. I think they have stepped into an area that we had identified in the interagency themes as being underfunded. Because again, people who wanted to do quantum computer science, wanted to do quantum algorithms, they really had limited places where they could go. There was some funding from NSF and everything else. And I think the DOE is designing its program around addressing this niche area that you and others have questioned. And so I think with time we will see that blossom. We will see some of this coming on. But again, I will come back to, because we're talking about this at the HPC. Jack Dungera maintains all the BLAS stuff and everything else, and helps every new version of a high-performance computer come out to port it and to make it efficient. And a lot of effort has gone in to allow that efficient portability. But if you look at the other application spaces in HPCC, there is no system to actually help port it. I mean, we lack that capability. So in some ways, it is a problem you already have, and it's going to come here. I don't know whether it will be as bad or not. I mean, I don't think we can imagine, but I think steps are being taken to address it.
So some of my best students working in that field have a background in computational science. Because those students know classical computing, they know HPC, they know application areas, and they know enough quantum physics to start. And they get productive immediately. So, and they then come with ideas from HPC about co-design, about auto-tuning, about good libraries, abstractions, and so on. So that moves in, and I think this will be important for the software stack. I think will follow what we learn from HPC there. But we need more computational scientists in general, and all of them should learn quantum computing at the latest at the master level.
So I might add that, lots of good comments, I agree with it. I think, in my humble opinion, we have a relatively recent experience in HPC that I hope we can learn from as a negative experience and not a positive experience. And that is when distributed memory systems emerged, the first standard that really happened was MPI. And that was a low-level interface that, again, in my opinion, was too close to the hardware and did not permit enough hardware experimentation below the standard that most people would be able to take advantage of it. So I didn't say that very well. Let me say it from a different point of view. With an interface, in my opinion, you want to find the middle ground where the users of the interface can get done what they need to get done, and there's enough design flexibility below the interface that system developers have great leeway to improve the system based on what's actually possible at the hardware and system software level. And I don't think we did that with MPI. And I think it hurt the industry, slowed down the industry, contributed to HPC is really hard to do because MPI is really hard to do. And so I think there is a lesson that we really need to think about this. And it's very hard because we don't have perfect visibility into what the hardware is going to look like in 3 years or 8 years. And it requires some of that.
Another lesson I would take that's perhaps on the negative side is transition, I think, in HPC from being supercomputing to being a broadly applied approach to computing. There are many, many, many users and applications that are really computationally expensive but not implemented on supercomputers. They were enabled by things like Hadoop, for example. Big data analytics is very demanding and a great use of compute resources for value, not a supercomputer application in a traditional sense. No one would dream of doing that in MPI. It was a challenge to move from large-scale, high-performance computing being an art of a few on a few large machines to much more broadly available and useful in programming model, in machine design, in infrastructure design. I think we'll face the same thing here. How do we make programming models, how do we make libraries, languages, etc., that help people the way we had to figure out ways to help people avoid the pitfalls of concurrency and communication and orchestration to avoid the difficulties that we do in strong scaling on supercomputers.
I think any lessons that we can learn, I'd love to hear the lessons that you guys have learned. I think one of the things that I'm trying very hard to do is people have this view that software and hardware are different. I think in quantum it's very much the case, especially when error correction and things like this come in, that there is no difference between them. It's all going to happen together. And I think the near-term applications are going to be even more. So I follow up on Matthias's point. We need more people with computation experience, and it's going to be an architect that's going to be a little bit blurry between the traditional differentiations that people have at the moment.
So I'll just add to this. I mean, because all you have to do is go back and look at the early classical computers, and they had hardware error correction and everything else. I mean, and quantum merges this together. As the technology builds out, we will find clever ways around some of this stuff. But I mean, the early stuff is going to. I think, you know, if you come back in and you look at the number of groups that have the number of companies here today who talked about having a vertically integrated a program, I think that points to this key point that you know, in the near term, because you can get just a little more out of that early quantum 496 or 486 or whatever chip, you know, by getting down into the hardware and optimizing a few gates and the layout of your program and everything else. And so they're going to go fine tune it the same way people who really want that extra 10 or 20% on high performance computing go fine tune. And so I think that at least in the early years, this is the way progress will be made.
I'll just comment on something else that came up here, that many of the speedups that we do know for quantum computing rely on some assumptions that the computations happen in a fully parallel way. That if you try to, like, for instance, if you try to take quantum computing and stick it into a traditional, like, Harvard architecture model where you have some local compute resource and a large memory and the data gets moved in there and gets moved back, all the proofs about quantum speedups evaporate immediately. So you really have to be thinking of this completely parallel system, which immediately stresses out all these learnings that people have had trying to build distributed systems for high-performance computing. So we're aware to some degree of the things that have been tried before through things like MPI, and we're trying not to fall into the same traps. But I think there is an element to what we're trying to do here, which requires going down this parallel model, distributed computing model, which necessarily makes the problem a little bit more difficult than you might necessarily like.
All right. I'll ask another question because I do have a million. If you look at this data summary sheet of the Department of Energy's latest budget request, if you will, under the quantum $100 million plus up, They use the phrase emerging urgency of building U.S. competency and competitiveness. Now, those are great words when you want to sell something to the Hill, but what it does signal is that the U.S. government feels it's in a position to help the quantum computing sector. So for 5/7 of the panel up here, what are some of the things you think the U.S. government could do to help you with competency and competitiveness? And for the other 2/7, what are some of the things that you think the U.S. government can offer that could help in this realm? The HPC sector has a long history of cooperation with the federal government, primarily due to national security agenda, where technology, research, and procurement, and even was integral to the emergence of the sector. Does that same kind of situation exist here? Or what are the kinds of things you would like to see the U.S. government do? Because some of them are here right now and they're listening. And this is an opportunity to say, this is what we'd really benefit most from.
I can think of quite a few. Just the first few that comes to mind is to be a customer, not just of the long-term fault-tolerant quantum computing application areas, but also the near-term approaches. Help us make these resources available to researchers in the universities. Another thing is, what we're trying to do to actually get to the fault-tolerant regime is going to require potentially radically different things than what we're doing today. Different qubits, different methodologies for connecting them, different signal delivery methods, and most of those things are going to probably come from the academic space, from researchers doing basic research, as opposed to just engineering the next milestone. So definitely, we can't let the foot off the gas in terms of funding basic research in quantum information science.
I agree quite a lot with Blake. I think the US government has put a lot of effort into quantum computing. I don't think we would be here without what they've done, to be perfectly honest. But continuing to put more effort into things that are not the traditional way of building up towards fault tolerance would be good. But also, I think we need a lot more effort into understanding truly the overhead of fault tolerance. Even putting, how do we enable the people that understand codes from the classical side to come and start thinking more about codes? Like, I think people have this view that we've solved error correction and we should just build up on some way. And this is not true. Like, we have some good codes, but there's a lot of work that needs to be done to bring that down.
Funding research, funding the education, advanced education, graduate education, being a customer, all of those things are good. I think you pointed out very rightly that there are areas where we have latched onto possible solutions where there are other alternatives that deserve exploration as well. And that's another area that I think there are contributions to be made. So I would also endorse what you said. Government has been investing in quantum for a long time. They have big investment. So it's a question of where might there be additional things, rather than being absent and suddenly doing something about it, which is somewhat the impression that the press about the government investment might give. The other thing is I'm interested in what those agencies believe they could do, because I think they'll have things to offer that we don't necessarily think about. I do want to make sure that it is something that doesn't slow down our efforts. It's easy to look for help or resources that end up having a cost in terms of attention and in terms of involvement that we really don't want to have happen, and I'm sure they don't want to have happen either.
So I guess I'm in the 2/7. So I think, there have been, if you will look, the number of workshops that the agencies have held in the last couple of years, there's been a lot of engagement out with industry and academia trying to understand from them where we need to go. We also, independent of that, have identified some key roadblocks. And mostly when we come back to them, they have confirmed those roadblocks. And the issue of workforce, especially the fact that until the last few years, there was an overabundance of physicists and an underabundance of people either from the engineering field or from the computer science field. Again, we've worked, and I think we are beginning to make progress on that. Again, I know my error correction expert inside NIST, Manny Keneal, has told me, when people get to this point of view and they want to know exactly what error correction code to use, they should come back to me. Why? Because he actually has come up with several of these things. He understands this space quite well, and he will come back and try to help address that problem. Those problems do exist. There was a comment down here about transduction. Again, everyone's out there is sitting with their computer or their smartphone, and mostly what these devices do is they transduce information and move it around in different modalities. And in the quantum space, we're going to have to do that same thing. And this is a common problem, again, where we can come back in because it isn't the pressing issue that a lot of the big companies have, but that common transduction problem can get them better signals into their things. Part of talking about, again, a consortium is coming back and saying, what do you see, and help me come up with a prioritized list, because the government is not going to solve all the problems. What we can do is come back with the prioritized list and come back and try to address the most pressing problems and the problems that will have the biggest impact, because some of them are pressing, some of them have more impact. And we need to do some of both, and we need to figure out how to create a balanced portfolio. The other thing that we need to do is we need to increase our basic R&D spending to produce the workforce that is going to be absorbed. And notice I said to produce the workforce that is going to be absorbed. We don't want to overshoot this. I think there are other countries out who are throwing too much money too quickly. This is not a problem where I can throw a whole lot more money at this problem and I will get only an incremental increase in output. I need to be throwing the right amount of money both to solve the right problems and to produce the people that industry is going to require. And that means that we have to spend more time talking and engaging. I think the last thing that I think that is essential is there are a number of places where there are critical mass. Establishing more centers where there are critical mass. Some centers will focus on technologies, some of them will focus on quantum sensors, some of them will focus on something else. Establishing those centers, because if we look at the innovation cycle, what actually happens and when the startups come out is where there's already critical mass. And so we need to create the environment where it is. And that means for every company that is set up, and today if you go count, I believe there are roughly 25 venture capital started companies in the last 2 or 3 years created in the quantum space. Well, a few of them, like Rigetti, are a few more than 3 years. But if you look at that, there are 25 of them. There will be another 25. There will be another 50. And for everyone that's created, there will be for everyone that's created, there's going to be 0.95 that die. And they get bought up by others. This is part of the innovation cycle, and we need to make that work, and we need to support that innovation cycle and do the basic research that will help push this and make us develop the underlying technological infrastructure to actually win the game.
So I would strongly agree with what Blake said about the U.S. government should be a customer of a purchaser of systems, even in the pre-useful era, because I think it's true for all these systems that however useful they are when they're purchased, they'll be much more useful in the next generation. So I think that's an important thing. And I had a second point, which has left me. The third thing I think I would mention is, to be direct, being a Midwesterner, it seems like there are a lot of the government programs that have decided that gate model is the way to go, and that quantum annealing is not going to succeed and is not useful. And we have limited, I think we have to be a little more humble about how much insight we have into the future. And if we should be buying the systems and funding the systems that can be useful. And I think choosing an architecture at this stage is premature. Oh, I remembered the second thing I was going to say. So some of you may remember late 80s, early 90s. I think it was DARPA pushed most of this to the move to MPPs, the thinking machines, the early Intel hypercubes, et cetera. And the hardware made great progress, and then I want to say it was 92, 93, somewhere in there, somehow the realization came to mind that, oh, we're going to have applications to use these things, and nobody has funded that, and so we should fix that. And there were comments here from several people that said, gee, we need people thinking about how to use these machines, and that's applications, or I would view that as applications, and that's a separate thing from hardware, it's a separate thing from system software and tools, and it takes real time and real energy, and funding that as a distinct thing would be high value in my view.
Okay, great. Thank you very much. The big red clock on the desks tell me that we're actually out of time, so I'm going to release you guys all back into the wild. But I do want to thank you for your time and your insights and your dedication to a cool technology. And I hope that you're all willing to come back at some point in the future and tell us all the great leaps and bounds and progress that you folks have made. But otherwise, thank you so much for your participation here today.